Imagine this. If I ask you to multiply 999 times 888 times 777 in your head, you would probably smile or laugh. But 400 years ago, this was not a joke. Astronomers, sailors, and scientists had to do calculations far more complex than this every single day, without calculators, without computers, without shortcuts. So, how did they survive? They invented something extraordinary, something that turned multiplication into addition, division into subtraction, and helped humans measure the stars, navigate oceans, and understand natural disasters. That invention is called logarithms. And today we are going to discover why logarithms exist, how they work, and why they still matter. Let's go back to the early 1700s. There were no calculators, no Excel sheets, no digital tools. Astronomers were calculating distances between planets. Sailors were navigating across dangerous oceans. A single mistake could mean a wrong scientific conclusion or a lost ship. A Scottish mathematician named John Napier asked a powerful question, not how big are numbers, but instead, how do numbers grow? He noticed something remarkable. Repeated multiplication behaves like repeated addition if you look at it the right way. This idea changed everything. Logarithms were not discovered by accident, they were invented because humans needed a better way to deal with complexity. And this is the key theory of knowledge idea. Mathematics does not grow in isolation, it grows because of human needs. Let's make this very simple. You already understand exponents. For example, 2 raised to the power 3 is 8. Now a logarithm simply asks the reverse question. What power of 2 gives 8? The answer is 3. So we write log base 2 of 8 equals 3. That's all a logarithm does. It answers one question. What exponents do I need? Let's have another example. 10 squared is 100. So log base 10 of 100 is 2. Logarithms are not mysterious. They are just a different way of asking familiar questions. Now here is where logarithms become powerful. They follow 3 simple rules. First, log of a times b equals log a plus log b. Multiplication becomes addition. Second rule, log of a divided by b equals log a minus log b, which means division becomes subtraction. Third rule, log of a to the power n equals n times log a. Powers become multiplication. For scientists and sailors, this was revolutionary. Huge calculations collapsed into simple addition and subtraction. So this teaches us an important TOK lesson. The way we represent knowledge can change what is easy and what is difficult to know. Now let's talk about logarithmic functions. Consider the function y equals log base 10 of x. As x increases, y increases too, but very slowly. From 1 to 10, y increases by 1. From 10 to 100, y increases by 1. From 100 to 1000, y increases by 1 again. As x grows faster and faster, the logarithms grow slower and slower. That is why logarithms are used to describe extreme ranges, earthquake magnitudes, sound intensity, acidity on the pH scale, computers' data and information growth. Logarithms help us compress reality into something the human mind can handle. You might be wondering, if calculators exist, why should we learn logarithms? Because logarithms teach us something deeper. They teach us how growth behaves, how models simplify reality, and how mathematics connects numbers to the real world. Logarithms help us see patterns that are otherwise invisible. So the next time you see log of x, don't see it just as a formula. See a sailor finding direction, a scientist measuring the invisible, a thinker asking a deeper question. Is size important or is growth what really matters? Logarithms remind us that mathematics is not just about numbers, it is about understanding the world. And that is why logarithms still matter.